Hello everyone. In this lecture, I will be discussing about ripple counters. Counter is a sequential circuit consisting of set of flip-flops connected in a suitable manner to count the sequence of input pulses applied to it in a digital form. In other words, counter is a register that goes through a prescribed sequence of states on the application of the clock pulse. The sequence of states, it can follow a binary number sequence or any other sequence. The counter that follows the binary number sequence is referred as binary counter. An n-bit binary counter consists of n flip-flops and can count in binary from 0 to 2 power n minus 1. For example, a 3-bit binary counter consists of 3 flip-flops and it counts from 0 to 7. Counters are classified into two types, asynchronous counters and synchronous counters. In the asynchronous counter, the external clock signal is applied to the flip-flop holding the least significant bit. All the other flip-flops are triggered by the output from the previous flip-flop. Since the clock pulse ripples through the circuit, it is also called as ripple counters. Asynchronous counters, it requires minimum hardware, so it is easy to design and the speed it is low. In the synchronous counters, the clock pulse is applied to all the flip-flops simultaneously, so it is also referred as parallel counters. The speed it is higher compared to the asynchronous counters. So coming to the asynchronous up counter, it consists of a series of complementing flip-flops. The complementing flip-flop can be obtained by using JK flip-flop with J and K input tied together or using T flip-flop, that is toggle flip-flop with the input as logic 1. The figure shows the 3-bit asynchronous up counter. The A flip-flop holds the least significant bit. So the external clock signal is applied to A flip-flop and all the flip-flops receive the clock from the previous output. So QA is applied as a clock for B flip-flop and QB is applied as a clock for the C flip-flop and clock it is negative edge triggered. The J and K input are tied together and the input is given as logic 1. So with J and K is equal to 1, the output it is a complement of the previous state. The timing diagram of a 3-bit asynchronous up counter is shown in the figure. Initially, all the 3 flip-flops will be in the reset state. That is, all of them will hold the value 0. QA 0, QB 0 and QC is 0. The A flip-flop will be active during the negative edge of the clock. So at the negative edge, A flip-flop will be active. So with J is equal to 1 and K is equal to 1, the output will be complement of the previous value. Since the previous value is 0, the present value it is complement, that is equal to logic 1. It will remain in logic 1 until the next negative edge. So when it arrives at the next edge, again the A flip-flop will be active. So again the circuit toggles. So it toggles from logic 1 to logic 0. Similarly, at the negative edges, the circuit becomes active and it is toggling from present state to next state. QA, it is acting as a clock for QB. Initially, it is in 0 state. B flip-flop will be active at the negative edge of QA. So at this point, B will be active and again the toggling occurs. Logic 0 is changed into logic 1. This will remain unchanged till next negative edge. Again at the next negative edge, the circuit is becoming active. So logic 1 is toggled to logic 0. And QB is acting as a clock for QC. The circuit will remain in the initial state 0 until the negative edge of QB. So at this point, C flip-flop will be active and the circuit toggles from logic 0 to logic 1. The same process repeats. So the counter will count a sequence 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Again it comes back to 0 0 0. Next, asynchronous down counter. So these counter count in the downward direction, that is from maximum count to 0. The figure, it shows 3-bit ripple down counter. So it will have 8 states from 7 to 0. So it is going to count from 7, 6, 5, 4, 3, 2, 1, 0 and again back to 7. In up counter, the output QA is given as a clock for the next flip-flop, whereas in the down counter, the output QA bar is given as a clock for the next flip-flop. Similarly, the output QB bar is given as a clock for the next flip-flop. So in the down counter, the complemented output is given as the clock for the next flip-flop. And as usual, the flip-flop holding the LSB bit will receive the external clock. And again in this case, all the clock pulses are negative edge triggered. The timing diagram is shown in the figure. So for A flip-flop to be active, clock should be at negative edge. So at the negative edge of the clock, it is active. So the circuit toggles from logic 0 to logic 1. And similarly at the next negative edge, again A flip-flop is active. So toggling of logic 1 to logic 0 occurs. The same thing, it is repeated. And for B flip-flop, QA bar, it is acting as a clock. QA bar, it is acts as a clock for B flip-flop. So in this diagram, I have shown only the true outputs. So we can say that QB is active if QA bar goes from high to low, or else I can say QA goes from low to high. So QB is active when QA goes from low to high. So at this point, B flip-flop is active. So it changes its state from 0 to 1. So this 1 will remain unchanged till when QA changes from again low to high. Again at this point, B flip-flop is active. So again toggling occurs from logic 1 to logic 0. Similarly, the remaining clock pulses. And for C flip-flop, QB bar acts as a clock. So QC is active if QB bar goes from high to low, or we can say when QB goes from low to high. So C will be active when QB goes from low to high. So initially it is remaining in the 0 state, and the C flip-flop will be active when QB goes from low to high. So at this point, so again the circuit, it is active. So it changes from logic 0 to logic 1. It will remain in the 1 state till when again QB changes from low to high. Again at this point, C flip-flop is active. So again it toggles from logic 1 to logic 0. So in this way, it counts the value from 7 to 0. So this is 1117, 6, 5, 4, 3, 2, 1, 0 and again 7. The next type of counter, it is asynchronous up-down counter. So this counter, it counts in both directions, that is in upward as well as downward. So it is also referred as multimode counter. And this counter, it has two modes depending on the value of the control signal M. When M bit is equal to 0, it is acting as a up counter. So in this case, the true output, that is Q, is acting as a clock for the next flip-flop. And in the down counting mode, the control signal M bit is equal to 1. In this case, the complemented output Q bar is acting as a clock for the next flip-flop. The logic diagram for the asynchronous up-down counter is shown in the figure. So with m is equal to 0, it is acting as a up counter. So with m is equal to 0, so the output of the inverter is equal to 1. So with 1, the AND gate 1 and 3 will be active, and the AND gate 2 and 4 will be inactive. So QA will be connected to the clock of the next flip-flop. Similarly, QB will be connected to the clock for the next flip-flop. So the circuit, it acts like a up counter. Next, when m is equal to 1, it acts as a down counter. So with m is equal to 1, the output of the inverter is equal to 0. With the 0 as input, 1 and 3 will be inactive, whereas 2 and 4 AND gate will be active. So QA bar is connected as a clock for the B flip-flop, and QB bar will be connected as a clock for the C flip-flop. So it acts as a down counter. So asynchronous BCD counter, or it is also called as mod 10 counter. Since it consists of 10 states, it will count from 0 to 9. So once the state 9 is reached, it will again go back to 0. Here the circuit consists of 4 flip-flops, and it is again an up counter. Since there are 4 flip-flops, it will go from 0 to, it will go up to 16, but I need to stop up to 9, right? So when it is reaches a 10, that is when it reaches 1 0 1 0, the circuit should reset it to 0. So this can be done by using a NAND gate. So the input of the NAND gate, it is given from D as well as B. So when both B and D are is equal to 1, the output of the NAND gate will be equal to 0. That 0 is given as the input for clear input. Clear, it is an active low. So when it receives 0, the circuit will be cleared. So it will reach a state 0 0 0 0. Now we can see the timing diagram. So for A flip-flop, you will be having external clock. So initially it will be in the 0 state, and during the first negative edge, A flip-flop will be active. So toggling occurs. Logic 0 is toggled into logic 1. Similarly, for each negative edge, toggling occurs. So 1 it is changed to 0. Similarly, 0 change it to 1, 1 to 0. This occurs. Right? And for B flip-flop, QA, it is acting as a clock. Similarly, for C, QB is acting as a clock. And for D flip-flop, QC is acting as a clock. The procedure is same as that of your asynchronous up counter. The difference occurs only at this point. So when it reaches 1 0 0 1, the next count it is 1 0 1 0. So when this value, B value and D value, it is 1, the NAND gate output will be equal to 0. So the circuit is cleared to 0 0. This 1 0 1 0, it will remain only for a very few nanoseconds. So immediately it is going to 0 0 0 0, and again it comes back to 0 1 2 3 4 5 6 7 8 and 9. And we can cascade smaller asynchronous counters to construct larger asynchronous counters. So this figure shows a 6-bit counter constructed from two 3-bit counters. The output in the last flip-flop is acting as a clock for the next counter. So since 6-bit counter, it comes from 0 to 63. Similarly, mod 32 counter can be constructed by cascading mod 4 counter and mod 8 counter. Since mod 4 counter, it is having 4 states, so you will be having only 2 flip-flops. And since it is mod 8 counter, you will be having 8 states, so it requires 3 flip-flops. The output of this first flip-flop in the last stage, it is acting as a clock for the input in the next counter. Thank you. Happy learning.